بسم الله الرحمن الرحيم. صلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so this is lecture 4 in the course of deep learning for language modeling. And in the previous lecture, we talked about word embedding, which is introduction to embedding, how we can do it, find semantic similarity between different words. And today we're going to expand this to contextual embedding, and basically with the use of recurrent neural network, LSTM, and gated recurrent units. So this lecture is going to introduce the concept of contextual embedding and also the mechanics of recurrent neural network, long short-term memory networks, and also GRU networks, and how they contribute to the concept of contextual embedding. Okay. In the previous lecture, we have introduced different versions of predictive-based embedding, word-to-vec, which is a technique that learns the vector representation of words that are neighbors to each other, and using the dot product or the cosine similarity, we are able to retrieve the words that are similar. And there are skipgram and continuous bag of words as two different options. GLOVE provide a better contextual understanding as compared to word-to-vec, because word-to-vec only looks at the previous and the next element. However, in GLOVE, it leverages global occurrence statistics in the whole context, which capture relationship between the word based on how often they appear together in a large corpus. And also fast text, it's an improvement also of word-to-vec, incorporating the subword instead of using word for embedding, and providing better way to handle morphological variation in the language. But all these embedding, they do suffer from several limitations. What is this limitation? There is an important limitation that comes from predictive-based embedding.
Size or memory?
So this is one of the things. And another big limitation is that every word is going to have only one vector representation. And we have seen that in the language, the same word can mean different things. Okay? And this is because they are trained on simple, fully connected network. So at the end, every word is going to be to have only one representation. It's not going to learn from the context. Even if it repeats multiple times, we're going to consider, for example, in GLOVE, like the statistics. Yeah, I don't know who is there. I'm sorry, you have a lecture here. مش واحد يشوف من فوق. We are not listening to us. في محاضرة الحين. Okay. Okay, so now with recurrent neural network, LSTM, this problem can be overcome, and we need to have better type of embedding, which are contextual embedding. It means we are able to understand the word meaning based on its context. This is what it means. And the famous sentence where we use the word bank, and it can have different meaning, whether it has a financial meaning or something close to the river. They will have different meaning. So in contextual embedding, the same word can have different vector representation. This is the main difference. But before diving into this, in the traditional NLP, there is an important phase when we have a big corpus, is to do text pre-processing in NLP, depending on the task. Because RNN, LSTM, traditional approaches, they are very sensitive to the word variations. So if you want to understand the meaning of word, like for example, when we did word embedding, if we consider the word run and running, they are two different type of words. So maybe we can only consider the root to have the same meaning for different variations. And this is why, for example, fast text has used the subword technique in order to calculate the embedding of subword level instead of at the word level. So in order to get rid of this suffix and prefix and so on, traditional NLP techniques, they had a pipeline of pre-processing. You know, it can go through all of them or part of them depending on the complexity of the problem and also the complexity of the corpus. For example, if you start from a text, I love NLP processing 1, 2, 3 running, something like this, and I want to make sentiment analysis. So there are some words probably they are repeating multiple times and they don't bring meaning. So we can make some kind of text cleaning. If there are wrong words, well, something like this, so we can remove numbers. Numbers are not going to contribute to the sentiment analysis. So this is something that I can do. But now with transformers and large language model, we don't do this anymore, okay? Because they have much better capabilities to understand, you know, from the large corpus, all these different variations. But the LSTM RNN, they have better understanding than word-based embedding, but less understanding than pre-trained transformer models. So this is why we try to remove everything that we don't need, remove special characters, okay, we don't need it, and also making lowercase. Processing and processing in sentiment analysis is not going to have any difference, but if I train my model sometimes with this one, sometimes with this one, I may confuse that model. So this is part of the text cleaning, and then there is stemming and lemmatization, which is just keeping the root of the words, okay, original words, and this is after stemming. Instead of processing, we can process, running, run, and so on. So this is kind of much clean text. We're going to have the most important word that will affect the task that you will do. Of course, in text summarization, maybe we don't do, for example, removing special characters, or, you know, it depends on the task. But let's say sentiment analysis, what we have done is not going to, if we remove the numbers, is not going to contribute and affect the sentiment. And finally, tokenization. So you will have different tokens, maybe the root level or subword level. And then we do the same thing. We create a vocabulary. Every word will have an index. And then we will have a sentence. So sentences, although in NLP or recurrent neural network, we're going to train different type of sequence length. But for the sake of batch normalization, there is a technique called padding. And when there is a sentence that is lower than the maximum length, we're going to add a padding value. Okay, 0 here, it means a padding value. This is just for the efficiency of the training. It doesn't have an effect on the sentences themselves. But instead of training sentence by sentence, I want to train all of them. And you know, at the end, we're going to deal with matrices, and the matrices would have a fixed size. So this is why the input as sentence would have a maximum fixed size, which we know now in pre-trained models, the context length. But there is a difference, because in the context length in pre-trained model is fixed and it has to be always the same. But in RNN, they can deal with any sentence sequence length. But the padding here is for sake of efficiency. And finally, we will transform every word to embedding according to an embedding technique, and this will be the input to a recurrent neural network or an LSTM network. Okay, so later on, if I show you some examples with numbers like this, we assume that we started from text and we went through some variations of this text pre-processing technique until we have our embedding ready to be trained or to make inference. Okay, so how padding work in batch processing for recurrent neural network? We have several sentences. We're going to do the padding to fit the maximum size of the sequence. Now, if I have a sequence of size 4, if I have 2 words, I'm going to add padding here. And also, we don't want this padding to affect these sentences, so we can add mask. So later on in the training, these padding values will be ignored. So it's just a matter of formatting the input properly for batch processing later on, to be able to multiply by matrices without any issue. Okay, this is an implementation in PyTorch. Okay, you start putting your tensors. These are the indices. And then you use pad sequence. And at the end, you will have a padded sequence, as you have observed in the slide. So the key benefit This enables efficient batch processing. It maintains the sequence information, and the mask prevents the padding from affecting the computation. لأنه لو نستعمل هذا في الكمبيوتيشن يمكن يأثر لي على المعنى. Okay. At the end, the computer is not going to see pad value, is going to see a number. So if this number repeats, it's like part of the sentence. But we will put it as a pre-processing step, but we will remove it later on for training or for inference, not to affect the computation. And look at the difference here, why we do the padding. Now in batch processing, what does it mean batch processing? It means I'm going to process all information at once. For example, I will take a batch of 3, and this is going to be processed in parallel using matrix computation. Instead of multiplying single vectors by a matrix, I will multiply a matrix by a matrix. So this is how we do batch processing. And this computation is going to take, let's say, 1 time unit. But if I do it separately without padding, I mean, I can process this sequentially. I'm going to spend 3 times because this is going to be processed in parallel, and this is going to be processed sequentially. Here we have a batch size of 1. It used packet sequences and has variable length processing. On the other hand, here I will enable parallel processing, okay, given the GPU capabilities. It will lead to faster training and efficient memory usage. Okay, so this is basically just summary of what we've talked about. And this is the concept of masking. Okay, the padding tokens are ignored during processing. So the masking is the process of ignoring specific values, in our case, the padding values, which are assigned specific value. And it's commonly used to deal with variable length sequences in NLP tasks. And we usually use a special token, either 0 or pad, to be assigned to indicate that we have a padded value. And we use the mask to avoid processing unwanted tokens, so they don't affect the performance, and prevent padded value from affecting the learning, and also improve the efficiency. Okay, any question?
Any word with a 0 is padded. So we can't mix null with another word.
Which one?
For example, as soon as I have a word with a value 0, it means it's padded.
Yeah, of course. If 0 is special, is a special value. I mean, we're going to have a special token for the padding. Okay. It will be considered as as a padding, so it will be ignored. Okay. So recurrent neural network. Now, this is like the first technique we're going to start with. And the idea of recurrent network is designed to process sequential data in a sequence. It means if I have a sequence of 10 elements, I'm going to process the first element, then the second element, until I reach the 10th element. And it's recurrent because it's basically the same cell that is going to be invoked multiple times. But there is a difference, is that is going to take into account the previous state, which is the output of the previous iteration, as a new input into the new iteration. And this is what we call the hidden state mechanism. Okay, they maintain a hidden state that is updated at each time step. Well, hidden state هذا, it will affect the output at the next iteration. So this is kind of a contextual memory. احنا اشكالنا الآن contextual embedding. So I need to memorize the past باش يكون عنده تأثير for the future. Okay, for now I don't want to understand RNN as sample of equations, but what is the relation with the concept of contextual embedding and why it is better than the previous versions of word embedding and things like this. Okay, we did this in the previous lecture, but I want just to review the concepts. You know, a basic perceptron in a neural network is just a combination of a linear combination, Wx plus b, and then we apply a nonlinear function, sigmoid, for example, softmax if we have multi-class classification, and this is going to give an output, and you have a loss function to do a back propagation and optimize your weight. Okay, we want to minimize the loss or the error between the predicted output and the real output, because here this is the context of supervised learning. To generalize the perceptron, we have feed-forward network, which is basically a combination of multiple perceptrons. All of them, they will do same computations, and they will learn different patterns. And this is the way that we have used it to learn predictive embedding. Word2Vec, it works like this. I give an input, for example, different words in a sentence, and I want to predict the missing word. Okay, so the embedding for that word, it will be an embedding representation, vector representation, based on the context that it has learned from the corpus. Okay, this is Word2Vec. It's based on feed-forward neural network of one layer to learn the contextual representation of words based on the corpus. But what is the problem with this one? We know that in natural language processing, the sequence between words, it affects the meaning. And this is what was missing before into the Word2Vec and GLOVE. We don't have any meaning because we have only one perceptron that will just take cause to effect based on a single forward pass. So if I have a sentence like this, like starting from x0, x1, مثلا, I like this game, or I like AI, or whatever, we can process every word alone here. And it's like there is no relationship between these words into the sentence. And this is because in a feed-forward network, we have the output is just a function of the input. There is no effect of a history or a memory or something like this. So what is the idea of RNN? Is instead of relying on the previous version, I will process things in sequence. I will start by processing x0. It's going to give me an output. And this output, I will consider that it will be also an input combined by this output. What happens now? This output is not going only to be dependent on x1, but will be dependent also on x0 from the information that is coming from this perceptron. Because this perceptron, you can think about h0 is kind of information, a feature that is calculated. And this feature is going to impact the computation here. And the same thing when I will do the forward pass. So I'm going to have h1, which also impact x2. So you can see as you propagate, every hidden value is going to bring some information from the past. But okay, of course, this is a big advantage, but still it has a disadvantage that this information, after some time, it might be forgotten as it moves forward, because the impact of newer information will be bigger than what was in the past. Okay, so it solves the problem of memory, but to some extent. Okay, this is one of the issues that we will talk about deeper later on. So the idea here is that the output will be just a function from the input and the hidden state, which is the memory. Okay. And this is the representation. You know, this representation is exactly the same as this one. And this is why we call it recurrent. So when you see this one, it's not in parallel, it's in sequence. We run this one, and then we run the second. So all these steps will be pending until we process the previous ones. And looking at this one, you know, you will have xt will take the previous hidden state, ht minus 1, to provide the output y hat. This is like the abstract representation of recurrent neural network. Any question? واضح? So all the concept of context, it's what the memory is going to bring me in addition. Okay? So when I have a sentence and I'm able to memorize the words around a certain other word, so in this case, I can have better contextual representation of the word. Yeah.
HT is the output of
Yeah, ht minus 1 here is the output of the previous cell. Look at this one here. When I calculate y1, it will be a function of x1 and h0. And what is h0? It's the information that I have captured from the first iteration. At the end, I'm going to have vectors. And these vectors will have operation. And the output, you can think about as a feature or an information that will have an impact on the next one. So when we train on a large amount of data, okay, we are able to understand better contextual relationship. وهذاك علاش ال RNN وال LSTM, they have succeeded in simple tasks like sentiment analysis. Okay, sentiment analysis, مثلا, if you say I like NLP, well, you say I do not like. If you say I do like NLP or I do not like NLP, the word not that comes in the middle, it has a contextual meaning. Now, when it learns, okay, when we do sentiment analysis, we're going to map every sentence to a number 0 or 1. It's going to learn that, the occurrence of this word in this context, it may change, okay, the semantic or the sentiment level of the sentence. Okay, because it's going to consider both the effect of each word and also its order in the sequence. Okay, so both we have the RNN are good because they can maintain the order of the sequence. This is why we don't need to have any kind of additional position information. مش مثل transformer. Transformer, we need to explicitly mention the position of each word in the sentence. But here the position is implicit because of the sequential execution of the cells.
Doctor, is it computationally expensive? Is it computationally expensive?
Yes, because it's sequential. وهذاك من الإشكاليات اللي خلت الناس تمشي ترانسفورمر فيما بعد. Okay. So this is a clear example about how an RNN cell works. This is what happened exactly. When we start with an RNN cell like this, you will have a hidden state initially equal to 0. I don't have any prior information, so it's 0. And you will have an input vector you can think about as an embedding of a word, for example. Like I did in pre-processing, we're going to convert every word to an embedding, so it's going to be something like this. And it will go through computation, linear computation. We have a weight matrix that will affect the input. And I will have now another weight matrix that will affect the hidden state. And of course, these are learnable parameters. In the beginning, they start with being random. So they will give wrong output. For example, in sentiment analysis, if it gives, instead of giving 1, it may give 0.3. So there is an error. Of course, back propagation is going to adjust these weights to make them predict much better. And there is a bias that we can add, same thing. And here we apply a nonlinear function, which can be sigmoid, tan h. But the nonlinear function is something really important. I will have many slides explaining the role. But now just understand what is the computational flow of RNN. So at the end, the output will be this linear combination, multiply this matrix, this vector by this matrix, multiply this vector by this matrix. I will add the bias, and then I will apply a nonlinear function. And then this is what? This output will be considered like the hidden state of the next iteration. And now if you look at the two-step sequential workflow of our RNN, it's like this. This is the same I presented. Now I have a hidden state. This hidden state is the same as this one. I will take a new input. This is the second word. And this is the information that it comes from the previous word. Combining both together. Look now, this combination, it has understanding of the current state and what happened in the past. And this is the concept of memory. The memory is carried out in this hidden state. Okay? And then it goes through the same computation again and provide another hidden state. And this is going to repeat multiple times until the end of the sentence. Does it make sense? So this is internally what happened. It's basically the same as a you can think about this as a perceptron. Okay, a perceptron, we have Wx plus B and non-linear function. But here we have Wx plus UH, which is, you include the hidden state, and finally the non-linear function. Yes? You can think about as a word, as a token, as a subword, it's just an input, It's an input. إذا كان اشتغلنا في مجال ثاني time series prediction, it will be maybe, I don't know, an event or a number or whatever. Okay, so we need to represent any input as a vector, and then we do this for processing. Yes, yes. Now this will be in sequence. This is like, if I consider this NLP, first word, second word, but instead of processing them separately, this word will be processed only after processing the previous one. And the information that comes from the previous one will be affecting the computation in the second stage. And this is going to happen for the next stages as well. Okay, now the activation function here. What are the activation functions that you know? Sigmoid, yes. Tan H. Relu. Okay, these are the three most famous. في ماني الآن أصبحوا موجودين. Why do you use sigmoid and not tan H in neural network or the opposite? Do you know the meaning of each one?
Sigmoid for binary.
For binary, okay.
For linear also.
Hmm? They are non-linear. They are all non-linear function.
It depends on the application.
مثلا الآن في الكمبيوتر فيجن most of them they use ReLU مع sigmoid. I didn't see tan H في الكمبيوتر فيجن, but it's more in NLP, for example. Why?
Because the past cannot be 0 or 1. And in what like there's no negative.
Okay.
So in damage the computation calculation of an exponential.
يستعملوا في NLP. If you want to build a neural network, مثلا yourself, fully connected, what activation function you will use? You didn't think about it.
No, I mean,
Depends on
application.
classification or regression.
Okay, what's the difference if you want to use classification or regression?
They can classification they call sigmoid. They can binary. They can linear regression.
No, I mean inside the hidden layers,
Yeah.
not in the output. In the output, you'll use sigmoid for binary or softmax for multi-class classification.
They usually use ReLU.
Huh?
They usually use ReLU.
إيه حتى في الريجريشن بعض الأحيان استعملوا أصلا binary classification is a regression, and it's a value between 0 and 1, and then you make a threshold. Okay? Why I don't use tan H at the end مثلا؟ ممكن نعمل regression بالtan H. Yeah, now I want just to trigger this question because I'm going to discuss after المغرب أنه every activation function it has some kind of semantic, فيها logic معينة. واللوجيك هي اللي تأثر في اختيارها rightly in the model. لأنه بعد لما ندرسوا ال LSTM فيه سيل تستعمل tan H وسيل تستعمل sigmoid. You say okay, why? And I want to anticipate on the why, so later on when we talk about LSTM in particular, to understand better the choice of these activation functions. Okay. وين وصلنا لهنا؟ اوكي هذا بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, coming back to the RNN cell computation flow. So it's basically simple, same linear transformation, but look now we don't have a sigmoid like we used to have in perceptron, but we have tan H. So the HT, this is the new current hidden state, which is this one. This is corresponds to HT. XT is the input. This is my word as an embedding vector. And we have WH and WX, which is W and U here, which are the weight matrix for the hidden state and also for the input. And the bias term, which is this one. So basically, just an extension of normal perceptron, but it will work in recurrence, okay? Because the input of one cell, okay, in one iteration will be also added to the input of the second one as a hidden state, okay? And this is like a feature that we calculate from the previous state. It will contain a certain amount of information that they will need to carry out. And in RNN, usually we apply tan H, because tan H has a special meaning, as we will discuss now in a while. So before continuing with RNN, I would like to put a focus on activation functions and their importance. So we will introduce the nonlinearity to neural network. The activation function introduce the concept of nonlinearity, enabling complex pattern recognition to be learned. Now imagine that we don't use a nonlinear function. So just having a linear combination of the features, you won't learn anything. It's going to be proportional. So even if you do the backward propagation, that is not something to learn, no pattern, because of the proportionality. So we need to introduce a nonlinear function. So regardless of which nonlinear function, it has to be there with some characteristics. But these characteristics of the linear function will affect on the learning style and what kind of information we will have out of this nonlinear function. And the three popular ones that you have already talked about them is the sigmoid, which is basically calculation of probability. But this probability, it can have different interpretations. One of the interpretations is the logistic regression. Okay, can tell you whether the value is 0 or 1, or something in between if I wanted to consider as a regression function. We have ReLU, which provides fast computation and helps mitigate vanishing gradient issue in deeper network. This is why it's used in deep convolution neural network in general. And tan H, it converts any value between -1 and 1 and help to mitigate also vanishing gradient problem in RNN. And let's see how. So this is a summary of the three functions and their shapes. So this is tan H. Tan H of x is basically exponential x minus exponential minus x, and then the sum of exponential x plus exponential minus x, and this gives the values between -1 and 1. So look, if you have an actual value on the x-axis, if it goes to infinity, the maximum value you're going to get here is just 1. And if you go toward minus infinity, you know, very quickly you're going to go to -1. So we have -1 is maximum, 1 is maximum, and 0 is like the neutral here value. The sigmoid, this is the expression of the sigmoid, and it has a value between 0 and 1. So it will map any float number to a value between 0 and 1. And 0 and 1 is known as probability. You know, this is like the most intuitive meaning of any value between 0 and 1. So we can think about as probabilities. And now in the concept of NLP, it has very special meaning, because if you have an output as 0, it means you have cancelled this information. Now, why we use this in computer vision? Because in computer vision, you can think about this x-axis as the scale of the pixel values, luminosity. You know that pixel value, if it is 0, if the pixel value is, it can be also -27 to 128 as a pixel value. So this can help cancelling the dark pixels and only keeping the information of the bright pixel. This is one of the interpretations, okay, of the sigmoid function. So at the end, it's going to let some part of the information and going to cancel some other part of the information that we consider non-helpful as a feature. Okay, so it has different type of interpretation. At the end, it's going to give values between 0 and 1. And we have ReLU. This one is going to consider every negative value, only keep positive values. Okay, so it's max, 0, and x. So here the slope will be equal to 1. And there are variations of ReLU, different variations. So the mathematical intuition here, the gradient flow, it's zero-centered and help prevent the vanishing gradient problem in deep neural network. This is how we calculate the gradient of tan h of x is equal to 1 minus tan h square of x. This is in the backward propagation because you need to calculate the gradients of every value. And you can think about this as a vector, and we calculate the gradient with respect to this function. This is how we calculate the gradient of the sigmoid, and the gradient of ReLU, it's 1 if x is positive and 0 if x is negative, because 1 is the slope of that value. And practical applications, so we use this in feature scaling, the tan h, in hidden state of NLP, and also it's symmetric, it has equal treatment of positive and negative input. In contrast to ReLU, it will cancel every kind of negative output. So we use it in deep network. It has a constant gradient, so the gradient is always 1, and positive value help with training very deep network. And also feature selection, because features that are not useful will be just cancelled out. Okay, so everyone, it has some particular type of usage, and it has to be carefully selected depending on the task that we want to achieve. Okay, so look here, it's used for feature selection, and here it's used for feature scaling, because you can scale it up or down, or whether positive or negative. Here it can be used for binary classification. It can be used also for LSTM network so we will see this in a while, and also in attention mechanism used to create soft attention weights summing to 1.
For computer vision, they use ReLU?
Yeah, ReLU.
Yeah, because of the pixels of the images.
Yes, yes. Sigmoid is usually at the end, toward the end, if it has binary classification or.
So the reason they use ReLU is to cancel all the negative.
Yes.
So they need the part.
Yes, yes. And even the convolution, they cancel out negative values when you do max pooling.
Yeah.
Okay, so all the low values are going to be cancelled out. Max pooling also just extract the brighter pixels.
Mm-hmm.
Okay, and average pooling, it can also capture some edges and smoothing out the features. So this summarizes why and when to use an activation function. So why to use it? It has zero-centered output centered around 0, and helping a balanced gradient flow. Can express both positive and negative effects. This is why it's used in NLP, in sentiment analysis. It's able to differentiate between different type of words, and good gradient flow for training. When to use it for hidden state in RNN, I'm going to explain this. When data has natural plus and minus relationship, okay, and for sentiment analysis, you have usually positive or negative sentiment. It's not a binary, okay, we think about as a binary classification, but the features, they need to have polarity, okay, whether it is located in the positive side or in the negative side. Because it's with tan h that we are going to learn the features, and with the sigmoid you're going to classify the features. Okay, so there are two different things. So this is responsible for learning inside RNN, not the sigmoid. The sigmoid, we use it for classification, binary classification, or softmax if we have multi-class classification. Okay, so sigmoid, binary classification tasks, attention weights, and we use it also in LSTM to filter out the information in memory. Some of the information is useful, some of the information is not useful, so the sigmoid can be used to forget the non-useful information, and we will see this later. And ReLU, it's for deep neural network, CNN, and modern transform architecture. And it's not used in RNN due to information loss with negative value, which we want to keep. Okay. So you can see now there are clear differences. with use, and now we have at least some understanding about why ReLU is not using NLP, why 10H is more suitable for NLP, and the role of sigmoid in between. And sigmoid is used in both because you have always classification or regression problem. These just additional slides that explain the previous one.
Doctor, there is that, I think, leaky ReLU of.
Yeah, there are many variations.
Yeah, it's also have the negative.
Yes.
So why we don't use it instead of 10H?
But you know, it's very small slope.
Yeah.
Yeah, it's something like very minimal. But in 10H you have equal distribution of positive states and negative states.
Okay.
The distribution is different. Okay? The leaky ReLU is just to allow some low, maybe priority information, maybe they can contribute to better feature understanding. Okay. مثلا عاوز نعمل كانسلنج لكل الدارك cells ممكن نخلي some of the cells with a certain weight. Okay, just maybe they can bring additional information خاصة مثلا attention when there are cluttered environments. I need to discern more complex features. Okay. So now let's look at an example of RNN for sentiment analysis, how it works as one of the downstream tasks of RNN. This is how it works in practice. I'm going to show you a block. Now imagine that I have I like AI. And we're going to assume that there is kind of embedding transformation of these words into embedding. And this is just gray, you know, these are still not executed. The first execution is going to start from here. We start from 0 hidden state. We do our computations, linear, non-linear, and we will have a hidden state here. Initially, this output is 0, and then if I move to the next, okay, this is how it works. These are the computations. Okay, W and weight. This is an expanded computation. Finally, we will find this value as an output, which will be this one. This one is the hidden state, and I will also plug a new input, like. So same thing, we will do the computation in second iteration in the same way, doing the same thing iteratively, and this is going to give an output that will be also fed to this value with this one until at the end we get the final result. Okay, so this one, this value, it's the last hidden state and it's the output of the recurrent neural. It's the final output of the recurrent neural network. And look here, it gives me 40% positive, 10% neutral, and 25% negative, for example. So I'm going to have probabilities at the end, and based on this, we can say, there is one missing slide, whether the output is positive or negative, okay? So we can assume that we have positive, neutral, negative probabilities, and based on this, we can decide which about the class. So RNN also is used in contextual understanding, whether contextual embedding. And the same sentence that we have used before, the bank by the river and the bank in the city. They have different meanings. Now the RNN, when it starts to process the sentence, it will start by the first word, okay? So the initial state, the RNN start each sentence. It will notice how the word bank appears in both sentences. Of course, we assume that it has already learned from many patterns, but we will have different contextual meaning. So as the RNN processes the bank, it initially has a neutral representation. Consider the bank is the same thing, whether in the first sentence or in the second sentence. Look, it's going to give probabilities to the meaning of this. So what does this represent? This represent, you know, like an approximation of an embedding. Let's say there is a feature that represents nature, there is a feature that represents finance, there is a feature that represents location. And initially when I see the word bank, the bank and the bank, so I don't have any context that comes afterward. So the RNN, when we train it on a large corpus, is going to adjust its weight such that it will have a better understanding about the context of what will come afterwards. So going further, the embedding representation is going to change. Okay, and now if I go further for this, the bank river will have like probability of 80% because of the river in nature. There is something related to nature, there is nothing related to finance, and also its location. So the position of the embedding is going to change. And same thing if I move forward into this direction for this sentence. Okay, so the bank in the city will have more probability toward the finance, location, and less for nature. So the RNN has created two distinct representation. Imagine that we have a network, or RNN network, that will learn this representation. At the end, every word will have a particular embedding depending on how it looks into the sentence.
And Doctor, the location it represents like how sure they are, like this is the percentage, or?
Yeah, at the end, a bank has a location regardless of its meaning.
Okay.
Okay, so this is how it is interpreted. So, this is just an example of word representation, of course, in two-dimensional space or three-dimensional space, but in reality it's much more complex. I mean, we can talk about 100-element space or maybe thousands of elements. Okay, it's not possible to visualize, but the idea is the same. It's to have a certain contextual meaning that will affect the vector representation of each word. Now a word doesn't have a vector representation by itself, but it has a vector representation within its context. وهذاك علاش يعطينا الآن much better understanding about the sentences, about many other applications that we will see later on. منها مثلا entity name recognition. How can I know the entity names within a sentence? Okay, يمكن بعض الأحيان اسم قد يعبر على entity قد يعبر على شيء something different. If I consider just a word direct mapping with a certain characteristic, it might not work in every type of context. So all the deal is about how we can integrate the context into the understanding of the tokens or of the words to have a better contextual representation.
Just to increase my understanding, so for example, hypothetically, the location would lay in which part of the graph? Like any part, like maybe the left.
Yeah, here it's not represented, it's a third dimension.
Third dimension.
Yeah, we made a projection of the two-dimensional space because the third dimensional space doesn't add any information because it's the same in both. واضح? So if I represent the third dimensional space as a z-axis, it's going to be like a plane for both because the probabilities are close to each other. Okay. So this is just represented in the two-dimensional space, finance and nature, which have the main difference. And this is just hypothetical, as you already mentioned, just to illustrate this in mind. But in reality, learning from a recognition network is going to converge to better contextual representation of the words, given their context. Okay, and this is a major improvement as compared to word embedding. What transformer that we're going to learn in the next is going to provide even much better representation as compared to RNN and its variants like LSTM later. Okay, so this gives you an idea about the evolution of language modeling. How I want you to just grasp how did we reach to pre-trained transformer models, and what are the limitations of previous models that made the evolution for the next ones. And in the previous lecture, we talked about word embedding. It's good, have good semantics, but still limited. I cannot use it to generate language. Why? It doesn't have good understanding of morphology. It doesn't have a good understanding about the word semantic within its context. Now, RNN, it has partially solved this problem. It has a good understanding of the context, less understanding than the morphology, because the stemming, we probably need to do stemming and different type of text cleaning to reduce the complexity, because they will try to find out the best relationships possible without having a lot of noise. So the RNN is not well suited for corpus with a lot of noise. And pre-trained transformer, they have already dramatically solved all these different type of problems. Okay, this is one of the ways on how to see RNN, because RNN, it can be taught for different type of downstream tests, but because in the context of language modeling, we need to understand these contextual representations. And these are the forward pass that you already introduced, simple, and we have the backward propagation. We need to calculate the loss, the derivative of the loss with respect to the hidden state, okay, from one cell to another until we try to minimize the loss. Okay, so RNN is good, but doesn't come without limitations. Now, you remember this slide. For example, if I have a long sentence, despite the cat's fear, the dog becomes its best friend. Now, this is going to go through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 iterations. Now, the information that will come from the third iteration at the stage of 12 will be very small. We're not going to have a good perception about all the information that comes. So, because the impact of this word will be much higher than the impact of this word, and this word, and this word. So, RNN suffers from the problem of memory in long sequences. This is one of the issues. It's a memory issue. It's not able to remember very well. The information is going to come non-significant. Okay, and this is a summary. Another problem, which is computation, it's the gradient instability, because the training channels, the gradient is going to be exposed to either exploding or vanishing into long sequences. There is no way to recover previous information. مثلا في convolution neural network, how did they overcome the problem of vanishing gradient? If you remember ResNet, تعرفون residual networks, residual network with ResNet 2015. So one of the ways that we do usually is normalization. There is another concept that is called skip connections. You know what is skip connection? Skip connection, it means when I'm going deeper, I will bring information from 2 layers before and inject it into the next layer. Why? So this will help. هذه مثل مسألة الميموري. Okay? I will augment the data. So even if the gradients are going to go to 0, adding additional data is going to reduce the problem of vanishing gradient and also add some additional memory to the concept of the variance of RNN. It's similar to this one. We try to bring information from the past, but on another channel, not through the right channel, the normal channel. And the channel you calculate your forward pass. Okay, I will make a shortcut from another place to augment the information that I carry from the past. Don't worry if it is a little bit abstract, but we're going to see this in detail. So we have a problem of gradient instability. We have a problem of backward propagation challenges. During the back propagation, the gradient computation become problematic as they are repeatedly multiplied through the network. And the variants like LSTM, it solves this, but also partially still, okay? And the white matrix dynamics and contextual memory limitation. This is what we've already talked about. And this takes us to the concept of long short-term memory, LSTM. And this characterized by 3 different type of gates, call them gates, which are operations that we do inside the LSTM cell to carry out some information in some of the ways. So we have a forget gate. It decides which information to forget and which information to pass it through. And الآن إيش الإشكال الأول؟ It's مشكلة الميموري. When the information flows, اللي كانت قديمة تنسى. فأنا I need to find a way on how I can bring additional information during the forward propagation process. Okay. So we will have a gate or an operation that will decide what is the information that we can forward next. Another one that will control how much new information to add. الآن أنا اخترت قلت المعلومة هذه جيدة مش نعمله sum عشان نضيفوها على المعلومات السابقة. Okay, this is how we do it. It's always we make the sum of vectors to merge all the information together. Okay. So this is the input gate. والoutput gate, it's what I will liberate in the output. هذه فكرة ال LSTM. باقي الآن نشوف. I would like to assess your understanding. The forget gate. So basically any gate, it's linear and non-linear transformation. What non-linear activation function you can use in the forget gate? Think about it.
I think tan H doctor, because it captures before and after, assuming the negative is before, positive is after.
أقرأ لي definition of the forget gate. Try to read the the definition. It decides which information
really okay.
to discard.
اللي فيها زيرو بعدين
Really, it's possible, like it has an issue. It goes straight and go to infinity.
Maybe sigmoid. Zero
I
and
think
one.
this is the last one.
Yeah, zero one no.
Okay.
هذا يعني خلاص classified either here or here binary.
It makes sense.
Yeah.
لأنه عندي 0 and 1.
Yeah.
1 I remember everything.
Yeah.
و0 discard everything.
لا بس رينو كان فيها زيرو وأذر صح؟
Other لكن other linear. عندي أنا أصلا عندي مشكلة stability of gradients. Okay. ف it doesn't fit the probability الآن. I can say I will take 50% of the information. 0% لأنه this is like an amount that will add to the input. Okay, it's like a percentage of history that I allow to go into the present. Okay, well, input gate.
Doctor, is there a condition which word that we want to forget and what we want to go and let's say to
Condition
go?
of what?
يعني هل في condition معينة ولا خلاص in general؟
هو it's deep learning, you know, it's just computation that converge with backpropagation. This is why sometimes it's a good intuition, but it's not really explainable. It's the amount of data and the power of backward propagation that at the end you'll have a machine that can predict well. Okay, like there is no rule.
Okay.
It's not rule based. It's completely black box, you know. Yeah. But we know how to build this black box. But sometimes we cannot explain why this black box works pretty much well, like the transformers. Okay. So the input gate and the output gate is kind of combination. But الآن على الأقل we understood that sigmoid has a property that can tell us what to keep, what to forget. And this is an important point. Then LSTM, by the way, it's very complicated, but let's try to make it very simple to understand. So this is the architecture. Okay, it might look complicated, but we're gonna get through it one by one. I think now, with your understanding with the activation function utility, you will be able to decode, at least partially, what is the forget gate here?
First one.
And an input, or hidden state, and they will get through here. So this is the information I will carry from the past. صح ولا لا؟ And it will go through the sigmoid, which will filter this information. And it will pass through here the amount of information that I can take on this line. شفتوا الآن أصبح عندي two lines، خطين. ممكن نعتبر هذا الخط السريع وهذا اللي يدخل في الأحياء. اوكي، الخط السريع الآن مش ياخذ معه أهم الأشياء. Most important thing. This is the information that I want to carry from the past. طبعا there are some ways on how to carry that. So the first operation I do, I will take whatever input I have and I will take some part of that information. Okay, so you can consider this as the line of the long memory. And this is the line of the short memory. And this is why we call it the long short term memory network, LSTM. And this was proposed in 2000. So it's quite an old, 25 years ago. We have tan H here. What's the role of tan H? Yeah, it's an activation function. It's value -1 and 1. So this is what is responsible for carrying out information. this is a filter. Well, this is the information that I will take information positive or negative, between -1 and 1. So whatever value it gets, I'm going to convert it between -1 and 1. So this will ensure stability of calculations, will ensure putting any information bounded within a certain boundary. Okay, so you can see now we're using the discrimination property of sigmoid, and you're using the balanced property of the tan H to manage the information. So this discrimination works as a filter, and this balanced distribution of information, I'm going to use it to carry out the information from my states. So this is why we use tan H in recurrent neural network, because of properties, because it will tell us how to keep the distribution of information bounded between -1 and 1 evenly, okay, based on its property. And if we understood this, everything else is an architecture of calculation. لأنه في many variants يتغيروا، هذه الأوريجينال. But later method transformer, it has an original version, and then it has go through many variations. Okay, so let's go through all of them one by one.
Is it okay to repeat شوية حسب؟
باش نشوفوها الآن بالجزئية. أنا فقط أعطيتكم overall understanding, and now we're going to take it operation by operation. Okay. What I want you to understand from this slide is that we have two roads for the information flow. This road is going to carry the long-term memory. شفت الآن كأنه طريق مختصر. وهذا باش يروح على تعقيدات to choose what kind of information I need to keep shortly from this state and its hidden state. But then everything is going to be combined. باش يخرج عندي نفس الشيء, the hidden state and the long-term memory here. Okay, نفس الشيء. It's going to bring long-term memory. I don't have only hidden state, but I have also another new component which is called the long-term memory that we carry. Okay, let's take it one by one. Okay, the core idea is the conveyor belt, هذا ولا الطريق السريع اللي نسميه للمعلومات مش تمر عن طريق الكوانتيتي CT. So it's the important information I want to bring, okay, to keep as much memory as possible, not going through this transformation that will make it less effective. Okay, لأنه هذا الترانسفورميشن يضاعف اللي قبل، لكن هذا كان طريق مختصر. وانتم شوفوا كيف نعملوا STT, how it is calculated. So we have forget gate, input gate, and output gate. Let's start, and these are the different gates and states calculations. So it looks complicated, right? A lot of equations and so on, but you will see it's very simple. Let's see how. Forget gate, which is only this part, takes a hidden state h-1 and the state xt, and will be calculated through a sigmoid function to only keep the information. So I will filter out non-important information and pass it as an ft, okay, which is the forget gate. And this is the first difficult equation. Okay, so we will use the property of the sigmoid, and the output will be sigmoid of the weights we have in the recurrent neural network, and this is the combination of ht and xt نستعمل الاثنين مع بعض plus my bias. This one.
What is it called again?
Forget gate. Forget لأنه it uses sigmoid to forget or to remember. Any question?
Why do you use sigmoid gate to forget while we said in our
شوف discrimination.
Yeah.
تسوي discrimination. شوف forget أي.
Yeah.
Everything في negative خلاص discriminated. Not contribute. إذا خرجت منها خلاص مش تخرج في البوزيتيف. It will keep important information only. What's my objective? Is to keep important information. So sigmoid, I will use the sigmoid property to keep this important information. طبعا أرقام هي في الأخير، لكن it will converge, okay, through the backward propagation to have some kind of a consistent behavior. Okay, so this is the beauty of understanding the properties of mathematical function to make sense in prediction. Okay, but if you change this one with another one, you know, you will have a different type of interpretation. This is why I started to have a big focus about the active. You all know many properties, but now applying this to here, if I didn't explain this with a focus, you might not get the idea very quickly. Okay, so this is why it's always important to look at the activation function and their role into a certain type of architecture. And the interpretation of sigmoid here is not the same as doing a regression or classification or binary or something else. They share some common sense, but you know, here it's mostly a discriminative behavior that allow to forget some non-important information and to keep the most important information. Okay. Now the second one. So can you interpret this? Don't look at the equation now, just look at this one. What's going to do?
We have an input.
So it's basically the same computation as this one.
Yes.
Okay? This is going to be called as an input here. Okay, and it will just, this initial input, it will bring the same important information as we had here. And what about this transformation?
It's the expression function.
Yeah. So this is the tan H, which will calculate the candidate state or the candidate information that I want to pass to the new state. احنا لو فسرنا التان H قلنا مش نستعملوها فيها properties تاع balanced distributions okay. فالآن I will calculate over two paths and then I will multiply both together. فهذا عبارة عن weight هذا. شفت الآن this is considered as a weight. It's probability at the end, values between 0 and 1. So we can consider them as weights between 0 and 1 over certain dimension. They will be multiplied by the information. فالinformation المهمة تبقى والinformation الأقل أهمية تضمح تدريجيا.
And you forgot also.
Yes, so they are not exactly 0 and 1, they are values in between. القاء 90% خلاص, it's an important information. Okay, so this is what we call candidate cell state. It will be multiplied by this weighted information, and will be added here. Look, فالآن يصبح عندك a new quantity of information and another weight here. تنشر من بعد what is happening. And this is the input T is sigmoid WI HT. So every gate will have its own weights and its own bias at a certain dimension. And the same thing we apply CT, C tilde of T tan H multiplied by the combination of this vector plus BC.
But Doctor, here you have used the sigmoid, so يعني it will have also the same thing, the same concept of forgetting and
Yes.
remembering.
The forget is, you know, it's only one operation of sigmoid.
Yeah, definitely.
But we will do the same thing in the next slide. And now we're going to use the forget to have like a weighted matrix, a weight matrix. You can think about the output of sigma as a weight. الويت سيكون between 0 and 1. فاللي يبدا قريب من 1 يأثر على quantity of information that we're going to select. واللي يبدا قريب من 0 مش يضاعف الانفورميشن. واضح؟ This is how it goes.
But if we have 0.5,
Yeah, I mean, we're going to have weights based on the learning. You don't decide. It's your data that will decide. Your data will be decide what will be kept as important and non-important.
هل أنا أحدد الثreshold؟
Yeah, this is all common sense. I mean, it's not mathematical rules.
Yes.
Because, you know, I will show you different architectures. Okay? But just understand, you know, if you understand a little bit the meaning of sigmoid and what it does, and tan H and what it does, you will grasp at least 80% of that. And look afterwards. We want to calculate. This is the context-aware output. Because, you know, we will take you know, this is the output of the previous phase. And this is FT multiplied by the previous memory, by the previous important information. فمش ناخذ الكومبينيشن نتاع القديم والجديد نجمعهم مع بعض فيعطيني new memory, new long term memory. اوكي؟ فهذا ايش يجمع الان؟ يجمع ما بين الانبوت القديم والهيدن ستيت. فهو عباره عن كما قلت لكم عندنا طريق سريع والطريق العادي بتاع الار ان ان اللي يمر على many operations. We do almost the same thing, but the type of weight here is kind of different because the type of weight will decide what information to keep and what information to forget, and multiplied by the quantity of information that they want to preserve. Normally this is going to be here, لكن ناخذ بعين الاعتبار القديم ايضا. شوف الميموري يجيني من تحت من الهيدن ستيت والانبوت وتجيني من فوق ايضا على الطريق السريع، فاصبح عندي كانه دبل ميموري، ولذلك علاش عندي لونج وشورت تيرم ميموري نتورك. هذه الشورت خاطر عندها علاقه بجديد، هذه جايه من بعيد جدا قديمه. اوكي، فهذه دائما محادثه at high level، تعطيك اهم الاشياء من فوق، وهذه دائما من تحت تاخذ الهيدن ستيت وتاخذ الكورنت وورد وتعمل فيهم ترانسفورميشن، لكن تغذي اللي فوق، تغذيها. فبهذه الطريقه اصبح عندي مسارين للتذكر، احسن طريقه ممكنه. طبعا هذا مبني على ويندو ايضا، there is a window size or to apply LSTM memory. اوكي، اوكي الان انتهيت من المسار الاعلى، لازم نعمل الشورت ميموري اللي هي الهيدن ستيت. فنفس الشيء sigmoid and I will apply time h اللي جاي من فوق، وهذا الكل يخرج هيدن ستيت جديد. فخرجت الان long memory، خرجت short memory اللي هو الهيدن ستيت.
دكتور هل تخرج ولا just a copy؟ من الاوتبوت.
باين هذه باش تجيك هيدن ستيت جديد calculated as the output of this اللي هو ht-1 xtwo plus b0 applied to sigmoid يعطيني هذه، ثم ct هذه اللي انا عملت لها calculation نعود نرجعها في المسار الاخر. اوكي، لكن هذه الان تاثيرها باش يكون اقوى لانه اخذت مباشره another turn على هذه applied turn h مع الويت ماتريكس اللي هنا. اوكي، فهم كلهم سيجمويد لكن applied on different quantity of information.
So دكتور يعني الحين جايب الشورت تيرم ميموري هنا، اوكي. So in each case some of the information will go or لا كل الانفورميشن يروحون هنا ويروحون هنا ويروحون هنا.
هي combination شوف there are multiple operations.
so كل الانفورميشن راح تروح in all the gates.
نعم.
يعني مو it will separate يعني split.
هذا الآن this is one block في ال LSTM one block.
Yeah.
يعني this is for one word.
Okay.
This is the processing of one vector.
So
اللي هو هذا xt. This is one vector. Think about it as a word. اوكي، الوورد هذا مثلا جاي قبله بروسيسنج اخر. شو باش يعطيني بروسيسنج اخر؟ باش يعطيني الذاكره الطويله والذاكره القصيره. This is how it operates. Now the easiest way to think about sigmoid is used to create a weight matrix that will decide how much information to carry. والtan h is used to create the new quantity of information. واضح ولا؟ أنا عندي tan h واحدة اللي أعطتني new quantity استخدمتها مع القديمة. أوكي؟ فهذه الآن weight matrix على الميموري القديم and this is a weight matrix على الشورت ميموري combine الاثنين مع بعض يعطيني CT. النيو شورت ميموري هي اللونج ميموري مع الويت ماتريكس اللي جاي منها. فهذه I will use it multiple times to create weight matrices and to create a new quantity of information and I will take the global quantity of information that I take ونخرجها من جديد. Okay? That's common sense. there is no like if and else statement that it works for some very good use cases. خاصة الآن من أغلب الاستعمالات حتى اللي تتفوق فيها ال LSTM على الترانسفورمر هي في التايم سيريز بريدكشن. حتى في بيبر كامل انه ال LSTM is better than transformers for time series prediction. لما يكون عندك مثلا you want to predict in the future the weather ولا the financial stock ولا whatever, the transformers they don't have the same performance as LSTM. احنا جربناها في ال trajectory prediction of drones. وجدنا حقيقة ان ال LSTM provide better performance than transformer to predict the trajectory of drone in real time in terms of accuracy. At the end, okay, this is how we calculate it, and you will have a new hidden state and a new long memory. Okay. And this is the whole stuff. Now there are different variations. ثم اللي يجتهدوا يقول لك خليني نجيب أنا من هذه ونجيبها في هذه. اللي نعمل الويت حتى مع الميموري القديمة. قلت لهم it's a common sense. You can do your think about connect, but this is now becomes very old. Okay, and then I will also bring information from here, and from here to here. They made additional gates, allow gate layers to directly observe the current cell state, enhancing contextual decision making. ولا بنزيد context أنا ما خسرت شيء. خلينا نجيب اللونج ميموري هذا ونزيدها في الكونتكست هذا يأثر عليه أكثر. Is it good or bad؟ طبعا يعملوا experiments وبنش ماركينج ووجدنا أفضل في الحالة هذه مش أفضل في الحالة الأخرى. It's based on tests يعني. There are different type of variations. Another one, here they have used forgotten input gate work in tandem, making joint decision in information flow. So they've taken here from the 4 gate and they multiplied by this value. ما أخذوش sigmoid واحدة أخرى هنا, but they bring the information from here. I forget a little bit about this operator. لكن أهم شيء الآن أنه the limitation of LSTM. So it's complex architecture. It's one of the most difficult concepts. It's not easy to understand. We want to make it intuitive to at least understand the overall working. It has multiple gates, input for gate output, making them computationally expensive. So everything is going to be also very expensive in terms of computation مقارنة مع RNN اللي فقط فيها one activation function 10H. It has high training time due to their complexity. LSTM require more training time and resources. Okay, longer convergence time, resource intensive training and higher computational cost. And memory consumption, نفس الشيء, large parameter space because every activation function will have weight matrices and a W على كل gate, pi's على كل gate, and this is going to be very expensive in terms of memory and resource constrained deployment. And still, it doesn't have any parallelization. Everything is sequential. نفس الإشكالية. Sequential processing, limited GPU utilization. حتى GPU ما استعملوهاش بكثرة. حتى we cannot work in parallel. حاجة نعملوها في GPU هي batch normalization في التريننج. Otherwise, we don't. We cannot leverage the performance of GPUs. Yes. So, one of the most famous variants of LSTM اللي هي gated recurrent units. It's simplified alternative, يعني it has less gates. So it was introduced as a more efficient and simpler variant of LSTM. It has fewer gates. Okay, it has only 2 gates, reset gate and the update gate. It has reduced computational cost. طبعا هنا حبوا يعالجوا مسألة computational cost فنقص في عدد الجيتس وحاولوا they keep still the same information. علاش قلت لكم you cannot explain. It's a matter of common sense what information you want to keep and what you want to forget and how you can do it. So the reset gate functionality decides how much of the previous hidden state to forget. So عند نفس الفكرة بتاع forget state gate, and we have also the reset state So the performance often converge more quickly, work well, and smaller than set. وفي الحقيقة احنا لما استعملنا التراجكتوري بريدكشن اوف درون استعملنا الجرو، يعني عملنا ترانسفورمر LSTM والجرو it was the best strategy. Then we have paper, it's recently published last month, if you want to read about these experiments that we did for trajectory prediction. And surprisingly, I was surprised that one of the papers already mentioned this, and we wanted to test it, so we started by doing transformer on time series predictions. It didn't work well. ويمكن من الأسباب أن الترانسفورمر يحتاج really a huge amount of data. هذوما مثلا ال LSTM و recurrent neural network, even with small amount of data, they can still converge. But with transformer, first of all, you need to have something that is pre-trained, and then you have to have a huge amount of data to be able to converge using the self-attention mechanisms that are inside. So how it works? Let me go step by step. We have the reset gate, which basically takes, it's the sigmoid of HT and XT. This is the reset gate. It takes XT and HT, the hidden state, and then apply the sigmoid function to it. And the reset gate controls how much past information to forget when computing the hidden state. هذا نفس الشيء اللي بالنسبة للforget. Okay, بسمينا هنا reset. It's the same computation here. بس ما في bias. Okay, we have removed the bias. The bias term here it was removed. Well, it can be added. Basically, the bias sometimes it can be removed in training, or it can be set back. This is the reset, and the next one is the update gate, which is the ZT. This one. It's the sigmoid of another. It's basically the same operation. Both they use sigmoid here. And it controls the information flow in the GRU, preserving the past context. But the way now, this is going to update the long memory from here, and then you will have another hidden state.
So there's no short memory.
Huh?
There's no short memory.
Yeah, it goes like this. Look, this is like the path of the long memory. But you know, the computation are much more simplified. As compared to the previous one, we have less. We had 3 sigmoid function in the LSTM. Here we have only one, but we still look. This is the same idea. You forget, and the same is going also to apply to the tan H. So this is like the CT that we calculated before. Okay, the output from here. So you can think about it's like a simplified version of the long-term memory. This one. And they combined both long-term and short-term all together into the same output. Okay, so they have a way on how to reconstruct and simplify at the same time the computation and reconstruct the information, and at the end we'll have balancing memory and the new output over here. Okay, and then the H tilde of T is the tan H of, this is like the weight matrix that they call it the weight matrix in the output of the sigmoid multiplied by the previous HT minus 1 and XT. So here was a reset was applied only to the hidden state. ما دخلتش فيها ال X. And ال X contributes لل tan H directly, okay. And the HT, which is the final output, is 1 minus ZT, because this is a probability, an inverse of this probability, multiplied by HT minus 1 plus ZT multiplied by HT. So it's another combination. And this is a slide that summarizes all the variation of the different steps of the GRU network. And now we come to this conclusion. So to summarize, we started from word embedding for getting similarity between individual words without any context. And today we have reviewed the three variations of recurrent neural network, the RNN, vanilla and RNN, the LSTM with long and short-term memory, and the gated recurrent units. And what is the benefit here in terms of embedding? They can provide better contextual understanding of the language. Okay, so that was a good milestone for language modeling at the time, because they can find better relationship. So through RNN, it perceives a hidden state. For LSTM, it also adds the concept of long memory. And some other variations like GRU also optimize the performance in terms of memory requirement and also speed of execution. But still, it was not sufficient to build what we know today as large language models. What are the limitations?
From what I understood, Doctor, if we have, for example, 3 states of LSTM, I might have information, target information in the first one. But when it comes to the second one, this importance lower. It might be go to the short memory and it can be forgotten. But in the third states, it's actually important. So we can lose some information, that important information, in one of the states, because in that specific states, it wasn't important.
Yes.
So that's one of the conclusions that I
Yes. Yeah, that's good. Excellent. That's correct. لكن الآن in terms of limitation, لماذا النماذج هذه were not sufficient to build ChatGPT مثلا ولا لا language model that you know today. ايش الليميتيشنز اللي موجودين؟
Parallelization, time.
عندنا مشكلة الباراليزيشن. They are sequential models. We need to execute the sentences, very long sentences with 1,000 words, one by one. Okay. عندنا حتى مشكلة الانefficiency في التريننج، لازم عندنا padding for batch normalization وبعدين you apply the mask. Okay, another thing. مشكلة الميموري. ايش مشكلة الميموري؟
And we will forget a lot of information.
Yeah, still even with LSTM it has a window size مثلا 20 words. وكان عندي جملة أنا مثلا بنعرف علاقات على 1000 كلمة 2000 كلمة. الآن الكونتكست سايز تشات جي بي تي يوصل 128,000 كلمة which is a huge. Okay, so it was trained to understand a context with 120k tokens. لكن with LSTM it has a limited size. لأنه في الأخير even if you increase the window size it's going to have very big cost in terms of memory and processing. Okay, so we can observe that these have lead challenges. أيضا the complexity of these models and the fact that they cannot be parallelized, they require to do pre-processing on the text to make it simpler. لكن في بعض الأحيان لما نعمل pre-processing نفقد كثير من خصائص اللغة، المورفولوجي نفقدوها. اوكي، نذكر كلمة أنا يلزمكموها لو باش نرجعها لزمة الفعل المجرد، خسرت 4-5 معاني في الكلمة. اوكي، فكل الأشياء هذه يعني it was limited but it has been successful in many applications مثل machine translation, speech recognition, text to speech, speech to text. So it was really successful in doing many of the things and proofreading, مثل Grammarly and whatever. So providing also contextual embedding vectors, sentiment analysis was very popular, but it was not sufficient to have a machine that can generate a language, it can generate words properly. And this is why Transformers is all you need was the milestone. And they were really successful in choosing the title, at least until now. We don't know what will be the technology in the future, because they were able to address all these different types of problems. First, the parallelization. كيف عملوا مسألة parallelization transformer? You know a little bit of transformer or no? Not really. Okay. فايش فكره الترانسفورمر؟ اول حاجه تخلصوا بالسيكونشال مودلز. رجعوا للنموذج الاول فيد فورورد نتورك. هذا اول شيء. ايش معنى فيد فورورد نتورك؟ ما هي خصائص الفيد فورورد نتورك؟ يس.
مود تنتقل يعني
هو الخاصيه فيكسد انبوت. فيكسد سايز انبوت. صح ولا لا؟ الدانس نيورال نتورك عندك input معرفش 100 value to 100 values, and this is why in transformer we have a fixed size input اللي هو context window. واضح؟ So basically to get rid of the sequential model we get back to feed forward. لأنه feed forward network you plug everything all together and then will be processed in parallel. كل الكلمات ندخلها مع بعض. لكن لازم يكون عندي حد اعلى لعدد الكلمات المسموح ادخالها. لانه في الاخير I will enter vectors. مثلا نقول I will have vector of 1000 token and every token will have an embedding vector of 100. So I will have a matrix 100 by 1000. That's my input. That's my input. Okay, so to make parallelization we don't process the things in sequence, so we process them in one batch. And I have a slide. So these are the issues that we've talked about. We summarize. Okay, and the encoding bottleneck, compressing all sequence information into a fixed size vector. هذا مسألة padding. Slow and no parallelization, we talked about it. And the short memory. هذا the three bottlenecks. لأنه in recurrent neural network and its variation, to ensure the concept of time, we need to process all this information as a sequence, one by one. Process this one x0, then x1, x2, until the last one. ففكرة الترانسفورمر, let's forget about this sequence, and we put all the text all together, and you will provide it into a module that will provide an output. That's the idea. فكل الفكرة الآن okay I will go back to feed forward network, لكن ال previous operations الموجودين activation function ولا convolution they didn't have the ability to find the relationship between the words. هذا كل مشكلة اللانجوج يجي العقاد بين الكلمات مش نستطيع نتكلم، مش نستطيع ننتج نص، لازم نفهم اللغة. فالفكرة أنه الآن غيروا في طريقة البروسيسنج في الفيتشر فيكتور هذا اكستراكشن باستخدام الاتنشن، مسألة الانتباه السيلف اتنشن. اوكي، اللي هو مبني على طبعا انفورميشن ريتريفال كونسبتس والدوت برودكت والسيميلاريتي والاشياء اللي درسناها ويل جو انتو ديتيلز، لكن فقط باش نفهموا احنا علاقات الاركتكتشر مع بعض، انه الترانسفورمر at the end will take everything and put it into a feature extraction. Okay, feature extraction هو اللي يجيب العلاقات بين الكلمات in some of the ways without having the need to go into sequential processing. لكن هنا مش يكون عندنا اشكال. شو هو الاشكال مش يكون عندنا؟ لما ندخل البيانات الكل مع بعض، ماذا سأفقد؟
accuracy؟
لا. كلمات. لا، نفقد الترتيب. إذا دخلت كلمات كل مع بعض وخلاص دخلوا كل مع بعض ما في ترتيب. كله اتس وان شوت. السيكونس كان يجيب لي الترتيب، شوف الكونسبت اوف تايم كان يجي على السيكونس لانه 1 باي 1، فهو دائما مش يتعود اذا جت الكلمه هذه الهيدن ستيت باش يحمل لي المعلومات بتاع الكلمات السابقه. ما عادش عندي هيدن ستيت. I don't have any hidden state. فلذلك الامبيدنج مفهومه تغير. ما عادش نعمل امبيدنج للفيكتور ولكن نعمل امبيدنج للفيكتور وللبوزيشن. كل بوزيشن عنده embedding vector هو اللي يحمل المعلومة، في الأخير يتجمعوا مع بعض. المعلومات إذا كان حبيت نحملها في النتورك نجمعها. الجمع في النيورال في الديب ليرنينج يعني دمج المعلومات مع بعض. It has a meaning. Okay. This is what we are going to learn, and this is like the ultimate milestone in language modeling is the textual representation, over a very large context. Now we don't have any limitation in terms of memory size. The only limitation is the context size. الكونتكست سايز بدأ صغير جدا. جي بي تي 2 بدأ على ثم بدأوا على 1024 2048 جي بي تي 3.5 4096 والآن وصلنا إلى 16884 توكن in the input. 128,000 في الاوتبوت 16,000 بس في الانبوت وصلنا 128,000. بعض اللانجوج موديل كان go up to 200,000. It means they were able to find a relationship in a context of 200,000 words in transformer architecture. Okay. فهذا was the history. انتقلنا بالتدريج. Next time we're going to spend a whole lecture about digesting all these concepts. We learned a lot now. I'm not going to go to transformer حتى اللي نعديه 3 next hours كلها practicing and implementation. I will try to make simple implementation until we build the full architecture of LSTM and recurrent neural network. Now in the remaining time, I made you some notebooks. I will share with you some notebooks that you